Right, good morning and welcome to our continued discussion on optimization problems. I want to do two problems and then we'll see where the time takes us. I want to do 10.6 next. A rectangular piece of cardboard with dimensions 12 by 24 is to be made into an open box, no lid, by cutting out squares from the corners and then turning up the sides. Find the size of the squares that should be cut out if the volume of the box has to be a maximum. Okay, let's get some drawing stuff happening and then we will see what we see. Okay, so now I want to do, whoopsie, touched random buttons, 10.6. And I want to draw a little diagram here. Let's get a square. Nice big square. And what's going to happen is I don't have a square. It's a rectangle. That's okay. Let's draw a rectangle. Okay. It is 12 by 24. Now I'm going to cut square pieces out of this and then fold it on these dotted lines. So let's do that. And by drawing and thinking, I am getting myself ready, thinking what are things that I've seen before, what are things that are new, and so on. So I like to take my time with this. There's no rush. Then I'm going to fold this up, right? So it's going to be a box and it's going to be folded up like so, something like that. So I need to, they ask specifically, what is the size of the square that needs to be cut out? So I'm going to let that length be X, and it's going to be everywhere. So let X represent the side length of the square or squares to cut out. Okay, because specifically they are asking for the dimensions of that square that I'm gonna cut out. And of course, once I know that, I know the dimensions of the box as well. Okay, so the 12 here represents, of course, the full length or width, and 24 the full length. If I'm going to fold it and I'm interested in the volume being a maximum, I'm going to have to talk about volume. So I'm going to have to bring in a letter. Let's use the familiar V to represent the volume, of course, of the folded box. Then I need my volume calculation, which is the area of the base times the height. Now, once I folded it up, it changes the length to the original 24 minus 2 X lengths that were cut out on either side. The width of the box is now 12 minus 2x, and the height or the depth is that exact square length that I'm folding up. It's going to be the depth of the box. So the volume is then going to be 24 minus 2x times 12 minus 2x times x. And I'll simplify that when I need to. I don't care about right now. I just want to have a calculation, a volume function that all depends on how much I cut out. So practically speaking, I am kind of restricted on what I can cut out to actually have a box. I can't cut out nothing. That's not going to work. If I cut out nothing, I have no volume. But what I can cut out can be very, very small, heading towards 0, but I can't have an equal, right? If I have an equal sign, then clearly the volume is going to be 0 because of this factor over here. How big can x get is the other endpoint that I need to consider. How big can it get? Well, what is the most I can cut out? Thinking about this practically. If I cut into this width of the sheet, of the rectangular sheet, that's only 12 wide. I'm cutting in here x, and I'm cutting another x on the other side. I can only cut in to halfway. So I can't really go any further than 6. Now I can't actually cut out 6 because then I have nothing left. So I'm going towards 6. And in this case, I can't really obtain these quote-unquote endpoints. They are boundary values, but I can't actually get them because if x was equal to 6, then I'd see from this factor over here that my volume is 0 again. So x is definitely bounded by these two from a practical standpoint. The function itself is a polynomial. It doesn't care what x is. It'll always have a value. But practically speaking, I have this extra restriction that I need to keep in mind at the end when I try and find my optimal solution. But before I consider the endpoints, I need to find the critical points. And in order to find the critical points, I need to take the derivative. And in order to take the derivative, I want my function to be in the nicest form possible. I don't know if it's necessary to do a whole product rule on this, just because my original setup of my function looked to be the product of 3 things. It doesn't mean I have to leave it like this. Maybe, because they're fairly simple. I want to multiply this in and FOIL it out and see what I get. Let's get these 2 brackets going. So then the first 2, let's just show something in the chat to have something to look at. Let's see if MathBot wants to work with me. 24 times 12. Since it doesn't, I don't need to be able to do that in my head. 288. That's the first ones. Then maybe the outside ones. 24 times 2x, or negative, will be negative 48x. Then the inside ones will be negative 24x. And then the last ones will be positive 4x squared. Of course, that's all multiplied by an x. I don't want to go too fast here and maybe run the risk of some people missing a step or anything. So let's see here. I want to put these guys together at least, and that's going to be a 72, isn't it? 48, 68, yeah, 72, and then times another x. So let's multiply that x in. 288x minus 72x squared plus 4x cubed. Now, even though it's a polynomial, I see that in practical situations, my numbers aren't that small anymore, and I don't want to graph this. Ew. Even if I could, it's an inefficient use of my time. Now, there is my function, right? Now, the derivative is quite straightforward. 288 minus 72 times 2 will be 144. And then the x, and then power rule and other main properties will give me 12x squared. So the derivative is a quadratic function, polynomial, so I don't have to worry about where it is undefined. In the cases where I know my function doesn't have any x values where it's undefined, I'm not going to write that every single time. I know to check where's the derivative 0 and undefined. In this case, there's only the 0 option. So I'll just set this equal to 0. Actually, I'm going to swap it around while I do that, because my quadratic formula is possibly coming. I want to write it in a way that makes me comfortable. And decreasing power of x helps me remember my quadratic formula. I'm not saying this can't be factored. I look at it, I'm like, maybe. Do I really care? If it's not obvious, then I don't truly care. But if you want to put an effort in, I put a few seconds in to see if I can factor it, because it would save me time if that answer is yes. And I can certainly take out a 12 everywhere. And then I have a 24. Maybe I want to just double check that 24. 288 divided by 12. Or maybe I'm confident. Regardless, of course, be sure you're factoring. And now I look at this. Can I quickly factor this? Maybe I can, maybe I can't. Or maybe in the moment I'm just not seeing it. People put way too much emphasis on factoring. When I have a quadratic formula to handle this, is it necessary? I don't really see very quickly. 8 and 3 wouldn't work. 6 and 4. No, I don't see it. I'm not saying it's not there. It's like I check, I spend a few seconds, I don't see it, I move on with my life. Now the 12 doesn't matter, right? I can divide both sides by 12. So it's at least a simpler quadratic function. So factoring out the 12 was definitely a good idea. Now, I don't see how to factor it. The quadratic formula will always work. So why spend time more than a few seconds? So negative b is 12 plus or minus square root of b squared is 144 minus 4 times a, which is just 1, times c, which is 24, over 2 times a, which is again just 1. I like to see what is inside the square root before doing a whole calculation. 144 minus 4 times 24. 144 minus 4 times 24. Random line, and I get 48, which then shows me why I couldn't factor it. It's not a nice integer. Okay, so x is equal to 12 plus root 48 over 2 and minus. Let's see what we get there. I'm just going to check my square root function. I don't use it often. Is it maybe this sometimes? Or usually it's this, but I'm not sure. Okay, that works. Okay, so now I'm ready for the first one. And you can calculate the minus one if you want to save some time. I'll do the plus one. So 12 plus square root of 48. And then another bracket, right? Divided by 2. 12 plus, check my brackets. Okay, it looks pretty good. Random line. 9.4641. Or, of course, there's one when I minus as well. At this stage, I have to just see the number and then be sure which ones I need to move forward with. So the minus one, bracket 12 minus square root 8, another bracket, oops, hopefully the capitals don't matter, divided by 2, 2.53, 2.53559 when I round it. All right. So when I look at my practical restriction, 0 to 6, I see that though this function didn't know, there is a critical point at 9 point something and at 2, but I can't cut out this much. So this one is not applicable for me and my problem. The function doesn't know that. So I only have this critical point that I'm interested in. Okay, so now we have another situation where I can't actually obtain the endpoints. I do want to be aware of them and just check if there isn't something weird happening, that I'm heading towards a larger volume than anything else. Chances are no, but I do want to be sure. So let's summarize what we have here. We have some x values and we have some volume values. We have our endpoint of 0, which we can't actually obtain, so I put it in brackets. Then we have our 2.5359, which we can obtain, and then we have our 6, which we can't obtain, the other extreme. Now when we look at our volume, we already said that we're going to get a 0 volume if I head towards those two boundary values, which, because we want to maximize, is not what we're interested in. So hopefully it's going to be this middle one. I have to go back up all the way to my volume. I'll pick the very first version, it's the nicest, and then calculate what is the volume. Now it's going to be a little bit annoying because I have a large decimal number, but it doesn't take that long. And definitely check that you can get the same answer right. What do I have here? 2.5358983. This should be fine. Times 12 minus 2 times 2.5358983 something, and then times that number again, 535898384. Maybe you have a memory function in your calculator. Maybe MathBot does as well. I don't even know. I rarely use it. Oh, it's not happy with something that I did. What did I do that upsets you, MathBot? 24 minus 2 times the number times 12 minus 2 times the number. Oh, I have a random bracket. That's better. My apologies for the random bracket. So moving up here, we have a volume of 332, and because I used many more decimals in a simple calculation, I'm confident in the 4 decimals that I have, though I was a little bit relaxed. I didn't use all my decimal points. The issue of how decimal values are lost in calculations is a really complicated one, so I don't want to get into that right now. Concluding sentence: the maximum volume is 332.5538. What was the units? I think it was centimeters. So cubic centimeters. When a 2.5359 by the same number square is cut out. And there we go. Straightforward. I just want to show something that has a different geometric topic of volume. Doesn't always have to be an area of some kind of shape. It could be a volume in some sort of box design. And there are other problems, of course, as well, that you can have a look at to see the variations, but it's still based on some geometry. Next up, let's see a slightly different kind of situation. I want, which number do I want? I want 10.12. 10.12. All right. A fence must be built in a large field to enclose a rectangular area of that much. One side of the area is bounded by an existing fence. No fence is needed there. Material for the fence costs $3 per meter for the two ends and $1.50 per meter for the side opposite the existing fence. Find the cost of the least expensive fence. Okay, so let's have a picture. Picture helps a whole bunch to get me ready for the situation. So I have an existing fence, and then I'm trying to fence a rectangular region that has a specific area. And then, of course, I need to know the dimensions here. Let's go maybe x for the two side lengths and y for the other one. Of course, I have to write a sentence to define that. Let x and y represent the dimensions of the field as shown. I don't need to be too detailed, but I need a sentence. My picture can help my sentence, but it does not stand alone. Right. Then I have the area there. I already have a number, so that's totally fine. They tell me that the area, so x times y, has to be 25,600. I don't need an area variable because it's a fixed number. And I also have this issue of cost. So my cost is going to be the function that I create. So I need to define, let's say, C for cost. Let C represent the total cost of the fence, of course. Then, without worrying about this extra information, just looking at the fence, the cost is going to be dependent on the length of x and the length of y. It is $3 per meter for the two ends. So $3 per meter, I have 2x meters of fencing on those sides. $1.50 per meter for the side opposite the existing fence. So $1.50 times that length, which is just a single y. Now I can clean this up for sure. 6x plus 1.5y, and that's pretty much it. So at this stage, you can think about practical restrictions. You can think about, same as the very first one we did, right? My variables x could shrink down close to 0, and then I have a very wide field horizontally based on my sketch. Or y could shrink down to 0, and then I have a very long, thin vertical field. But regardless, they both have to be greater than 0. As they head to 0, I get these extreme flat horizontal one or really thin upright vertical one. Okay. So let's move forward, realizing that again I have a function based on two variables. That's not going to go well. That's why they give me this extra bit of information. I can maybe solve for y. Why not? And then I'll have y equal to 25,600 over x. That then goes into here, into my function. And so I can get a function just of x, 6x plus 1.5 times 25,600 over x. Let's maybe clean that up a touch. Maybe just a little bit. 1.5 times that numerator. Let's see what that is. 38,400. 38,400 over x. All right. With a restriction on x, really being not too, I don't have to be too concerned to improve it, because I don't think if I can actually improve it by much here. If x gets really small, then based on this over here, y is going to blow up and approach infinity. But I am restricted a little bit, of course. I don't know my length of my fence or my space that I practically have available. They don't really tell me that. And as y gets really small, x is going to blow up to infinity. That's how I'm going to make this right-hand side smaller and smaller by letting x get ridiculously big. So it's sufficient, I think, in this case, to just stick to the classic x goes from 0 or between 0 and infinity. In both of those cases, an x very small will make the second term, the y value, blow up, and then the cost will blow up as well. An x very big will make the cost on that pieces of the fence blow up, and the cost will increase dramatically as well. And remember, we're trying to minimize the cost. So those extreme ends, as I approach them, I'm not going to be very cost effective, because I have a fixed area. So if I want to make a very, very flat and thin rectangular field by letting x get super small, in order to meet that area, it's going to have to be super wide, and the cost is not ideal. So let's see what is the ideal cost. Well, for that, I am going to have to take the derivative here to find the critical points. First one's easy, 6. Now this, remember here, I could say 38,400 times x to the negative 1. So it'll be negative 38,400 times x to the negative 2. Or you can streamline that right away and put it over x squared. Now here, I have two issues, and I need to check them. I'll do the undefined one first. It's undefined clearly when x is equal to 0. But equaling 0 is not a practical possibility for me. So I can ignore that moving on. And then I have the derivative equal to 0 option. I'll just set it equal to 0, because I know some people aren't super comfortable with these things based on your memory, how long ago you've done all these little algebra thingies. Let's just focus on that. What do I do here? Many options. Many. The safest one is to just merge this on the left-hand side, which you might have done when you simplified the derivative. Anyway, we chose not to. Put it over a common denominator x squared, and I get 6x squared minus 38,400. It's not necessary in this case, but perhaps your derivative, you made it look like this, which might not be a bad idea. And then I'll more clearly see, oh, bottom equaling 0 is a problem. And to make the whole thing 0, I have to have the numerator equal to 0, just to relate it to things we've seen before. Each of these in a rational function comes from the denominator and the numerator separately. So maybe this would look a little bit more familiar to write it from the start into a single fraction and then see it as a rational function, and that might be more familiar. Either way, I get this, and that's going to be plus or minus square root of 38,400 over 6. Now I'm not interested in the negative, right? Because x can't be a negative number. So technically when I do this, there are 2 critical points coming out of this, but I'm only interested in the negative one. Not interested in the negative one, only interested in the positive one. So x is going to be, let's see, what is the square root of that? Square root 38,400 divided by 6, close the bracket. Oh, that's nice, 80. 80. Or, I'll just emphasize here, negative 80, and this one is not applicable. So we get this guy. And he's really the only one. Let's just summarize that. X values and not volume. That was the previous question. Cost. I do have these extreme situations, but we've already said that the cost is going to blow up whenever x gets close in those directions, or head in those directions. The only thing of interest that fall within my practical restrictions is this 80. What does it cost? When x is 80, I can go to this function, but seeing it's going to be the answer, I might as well find y and look at this nice simple version of the cost function. So when x is 80, y is 25,600 divided by 80. Let's see, that is going to be, what did I just say? $25,600. So I can do that over here. Y is 320. And then I can go back to my cost here. I want to pick the simplest calculation. And the original version, the sort of original version of the cost is nicest. So I have 6 times 80 plus 1.5 times 320. And so we get, oh, I need 2 equal signs. Right. $960. And I know that the optimal value, whether it's a maximum or a minimum, can only occur at a critical point or near the endpoints. Now these are a little weird because I can't actually get there, but if it happened to approach a smaller value, then that's the one I would have to pick. But they both go up, and I'm looking to minimize cost. So we have our winner right there. Let's write our concluding sentence over here. The minimum cost of $960 is obtained with what's the field? A field of dimensions 80 by 320. Easy enough, I hope. Easy enough, I hope. A little different in the sense that I am minimizing something and still sort of having the geometry, rectangle, circle, box, whatever. But looking at the cost side of it, I can get a function that I have to minimize. So just adding some variety to the situation. Okay, so let's just see here. We have some time. I'll at least try and highlight the last one I can really think of that has a lot of variety that we haven't seen yet, 1018. We'll see how far we get. I think we can squeeze it in. Your company needs to design cylindrical metal containers with a volume of 16 cubic feet. The top and bottom will be made of a sturdy material that costs $2 per square foot, while the material of the side costs $1 per square foot. Find the radius, height, and the cost of the least expensive container. Okay. So we have a different geometrical shape, perhaps, that is worth seeing in an example, so that if I happen to put it in the test, it's not that strange. So what is this? 1018. So we have a cylinder that is straight still. So what do I need to know here? I'm going to have to know the radius of the top or bottom, and let's call the height h. So let r and h represent the dimensions of the can as shown. And then, of course, we know we're going to have a cost. Let's say C represents the total cost. Total. Let's try to go a little faster here because I'm not sure we can finish it so quickly if I talk about every little thing. Okay. So then, the cost is going to be, top and the bottom is $2 per square feet. $2 per square feet. And all the way around, the size is $1 per square foot. Okay. So, when I calculate the cost, I have to sort of separate the pieces here. I have the top and the bottom, radius r, and then if I cut the can and fold it out, I have a rectangular side. And all of those surfaces cost me some money. So I have 2 times the cost of the circle, and the cost of the circle is 2 times the area, $2 per unit area. So 2 times the area, and the area is pi r squared. So there's a couple of 2's floating around which could make things a little bit confusing. The area of a single circle, pi r squared. $2 per unit area, so multiplying those. Then I have 2 of the circles, top and bottom, so another 2. Plus, it's $1 per unit area on the side, so it's $1 times the area of this rectangle. Well, when I cut it and lay it out, it's a height h, length here, and the length of the other side of the rectangle is going to be the circumference of the circle, which is 2 pi r. So the area is 2 pi r h, because it's length times width for a rectangle, right? All right, so a little bit more, just like before, when we mix some shapes, we get stuff that's a little more complicated. Let's clean this up. Before we worry about the next step, I have a 4 pi r squared plus a 2 pi r h. Now they're a little bit more mixed, but I still see that the cost function right now depends on both the radius variable and the height variable. So I'm a little stuck, but they give me more information. Extra information is that I have to have a volume that is 16. Now, what is the volume of this can? This is a circular prism, which means the base, I have sides perpendicular to the base, and the top face is also the same as the bottom. So it's then the area of the base times the height. So pi r squared h equals 16. So you see that there are some geometric formulas that you need to know. Anything with a circle, anything with a rectangle, as well as combinations, making cylinders and stuff. Volume, area, surface area, circumference, all kinds of things. So now in this case, certainly h is the simplest one to solve, and it'll be 16 over pi r squared, which then goes in here. Now I didn't do my practical restriction considerations yet. It's very similar to before, that I can either, what's the two extremes? I can either have a super flat can, but because I have a volume that's fixed, it's going to have to be very wide. So h is going to be potentially close to 0, but it can't get to 0. Then I won't have a volume. As well as the radius can, or has to be a positive value. And if I let that shrink down to 0, the can is going to be super thin and super tall, because I have a fixed volume that I have to get. So a decrease in one is an increase in the other one, which you can see here as well. If the radius gets super small, the height's going to blow up. If the height gets super small, the radius is going to blow up. So I have a similar situation like before. But we're still in the process of rewriting the cost function to have just one variable. So again, the setup is the most difficult thing here. Once we have the function, then I think if we run out of time, it'll be totally okay. So we're going to write this in terms of h, right? No, the other way around. We're going to eliminate h, and we're going to write the function in terms of r. So the first part is already in terms of r, so that's good. Then a 2 pi r, and then what h is in terms of r, if I can write properly, 16 over pi r squared. I know for some I'm going a little bit fast, but you can always pause and rewatch the video later. I want to clean this up a little bit. I'm going to leave my 4 pi r squared alone. This pi cancels with that one r cancels with that one, and I have a 32 over r. That's actually not bad. And like before, like we said, r is just going to have a standard practical restriction. Can't actually meet those endpoints, but we do need to consider it. So that's not bad at all. This is a pretty okay function, actually. I'm hoping that there are critical points. Next, we want to take the derivative, which is quite straightforward, I would hope, at this stage for you. This is, again, r to the negative 1, so it'll be negative 32r squared at the bottom. Now, it's maybe not the worst idea to put this together now over an r squared. It'll be 8 pi r minus 32. Maybe that looks a little nicer, that you recognize it as a rational function. All right. That doesn't look right. This is a cubed. So that when I simplify it, I get 1r left, and then the next term is going to be right. Okay, that's good. So I have two checks that I need to mention. Whoops. The derivative can be undefined when r is equal to 0, but that's not applicable for me. I can't actually get a 0. So the only thing I'm really interested in is when this is equal to 0, and that's going to be when the numerator equals 0. So I solve for r. I get 32 over 8 pi, or 4 over pi, and therefore r is the cube root of 4 over pi. Whatever decimal number this is the decimal number it is. You can calculate on your calculator. It doesn't actually matter, right? We have a value. That's going to be our critical value. We're running out of time anyway, so it's not a big deal. Calculated, rounded to 4 decimal places. In our summary, we're pretty much done. It's all now just calculator stuff, right? We have a radius and a corresponding cost. We can't get the extreme values. If we do get close to those, where's my cost function? If we look at this guy, if we do get close to a small radius, the second term is going to blow up the cost. If we do get close to a big radius, the first term is going to blow up the cost. So either way, we're not cost effective in those extreme cases. It's going to get bigger and bigger. So this is just a reminder that the endpoints aren't where I want to be. This critical point is the only one that could possibly give me an answer. I'm going to let you do the calculation for you to calculate. But this is going to be the minimum cost. And of course, I have to also calculate the corresponding h value, but that's not hard to do. Well, unless you don't know the MathBot commands, I just use the relationship between h and r, plug it in, calculate h, and in your concluding sentence, you just have to write the full dimensions of the cylindrical can and the minimum cost as well. So I leave that to you since we're out of time, but it's all just calculator stuff. It shouldn't be a problem at all, but if it is, let me know and I can walk you through this last little bit. That is the end of our optimization. Please check the schedule to see what is next on our schedule, what you have to do on the upcoming days.